Quantum mechanics doesn't make sense because it has this spooky action at a distance. I'm sure you've heard this somewhere. Well, I have news for you. A physicist has shown, not just argued, but mathematically demonstrated that the reason we find quantum physics weird might be that the universe really has two times, 3 directions of space and 2 directions of time. And so the idea explains why quantum physics seems to act faster than light. Let's have a look. At the heart of quantum physics is a phenomenon called entanglement. That's a type of correlation between the properties of quantum particles. Correlation just means that if you measure the property of one of the particles, then that tells you something about the properties of the other particle, regardless of how far away the other particle is. Correlations across distances are not in themselves mysterious. The clocks on your phone and my phone are correlated because they're both supposed to tell the same time. What makes quantum entanglement special is that before you made the measurement, the particles had no definite property at all. It's only if you measure one particle that the other one instantaneously also takes on a property which must fit to the property of the first particle. This happens faster than light. If you assume that the particles already had the properties before you measured them, then that just does not agree with observations. It's this update upon measurement which Einstein called a spooky action at a distance. The spooky action is not the entanglement. The entanglement is just a way to reveal the spooky action. The spooky action is the faster-than-light update of the faraway particle. One way to explain this is to just accept that faster-than-light processes are indeed possible, but this creates a bunch of other problems. Most importantly, there's the problem that while the measurement update in quantum physics seems to happen faster than light, that still doesn't allow us to send any information faster than light. This is because in quantum physics, we can't predict what the outcome of the measurement will be. We just know that the measurement outcomes must be correlated, but you can't send a signal by making a measurement. Now, if you say, okay, I just allow a truly spooky, faster-than-light action, then why can we not use it for sending information? Well, the author has come up with the idea that quantum physics makes use of a second dimension of time. Einstein's familiar space-time has 3 dimensions of space and 1 dimension of time. The author just says, well, let's add another dimension of time. The thing is now that a particle which travels in the second dimension of time might not travel in our usual dimension of time at all. For us, it might go elsewhere instantaneously. Okay, but how does this solve the problem that we never observe this other than in a measurement process? For this, the author introduces a hidden field that lives in this 5-dimensional space-time. The field connects only entangled particles. So if you measure one of the particles, that can update the other particle, but you can't use the measurement device to force any new information into the field. This means that the only observable result which you get in the end is that, yes, the entangled particles are correlated as they should be, but no, you can't do anything else with the field. The most interesting part is, though, that this theory does not make exactly the same predictions as ordinary quantum mechanics. The author proposes an experiment with 2 independent sources of entangled photon pairs. Standard quantum mechanics says that the outcomes from the first experiment should have nothing to do with those from the second. If the second dimension of time really has this hidden field, then the experiments should have a tiny additional correlation, and that correlation depends on the distance. That said, this is not the first time a physicist has proposed extra dimensions of time, and the reason you haven't heard much of these ideas is that they come with problems. They can make the vacuum unstable, they can bring in time travel problems, and they completely mess up Einstein's theory of general relativity, which Albert doesn't like at all. Also, entanglement is not all there is to quantum physics, and I'd like to see further further checks that this idea is not in conflict with some observations already. I give this paper a 7 out of 10 on the bullshit meter. It's somewhat sketchy, it's left many problems unaddressed, and as you all know, personally I think there's an easier explanation for the supposed strangeness of quantum physics, but this is a genuinely new idea that qualifies as what I'd like to call beyond quantum physics. That's the quest to find a deeper explanation for the quantum effects that we observe. And if the author is right, maybe in 10 years I can waste 2 times. A group of astronomers say they've discovered giant UFOs flying around the moon. And they're saying aliens could be here any minute now. Or as the Daily Mail put it, scientists issue warning after spotting more than 20 giant UFOs racing across the moon. Don't worry, it's probably nothing. But I also have an interesting something for you to think about. Let's have a look. The astronomers pointed a 15-centimeter telescope at the moon, corrected the images for camera noise, and found some moving spots which they refer to as unidentified flying objects. They calculated that the UFOs are 20 to 40 kilometers across, some are shaped like giant rings, and they travel at up to 11 kilometers per second. The authors think, quote, UFOs demonstrate intelligent behavior, and we believe that the moon serves as a base for UFOs. They made their observations in September last year, so the aliens are taking their time. The paper's not peer-reviewed and comes from 3 researchers in Ukraine. 2 of them already made headlines 4 years ago when they claimed they'd observed extremely fast UFOs over Ukraine. Their own institution subsequently published a report saying that the authors had an error in their data analysis. The distance to the objects was much less than they thought, so the objects were much smaller and much slower. The new paper basically has the same problem. Some of these objects that they observed are barely at pixel resolution of their camera. The authors themselves write that one object has a size of 2 times 2 pixels, and with only one record, you have no way to determine the distance. They basically have no data. For all I can tell, they've observed dust. This so-called paper is so complete crap. They probably just wrote this to bait the Daily Mail. 2 times 2 pixels. Aliens are on the moon. It's exploded my bullshit meter. That said, people have been reporting strange lights and objects around the moon for a very long time. Some of those reports came from the Apollo astronauts, as you can read in the documents that the US government just put out in early August. For example, during Apollo 12, astronaut Alan Bean was on the moon and said he could see particles of light, flashes of light, sailing away into space. He said it looks like some of those things are escaping the moon. During Apollo 11, the astronauts saw some region near a crater light up. During the Apollo 17 flyover, geologist Harrison Schmitt suddenly said, "Hey, I just saw a flash on the lunar surface." There have been thousands of reports of reported moon irregularities. Some of those might be meteorite impacts or sunlight reflections, but some of them can't be explained that way. For example, in 2007, an Italian amateur astronomer filmed a dark circular object apparently crossing the surface of the moon. In 2020, someone else near Montreal filmed 3 elongated objects. In March 2024, a German astronomer filmed a fast dark object crossing the lunar disk that he could not identify. Yeah, no, I don't think any of these were alien spacecraft, but I do think it's very possible that sometime in the past billion years or so, extraterrestrials came by our solar system and had a look at our planet. And they'd most likely have done that from the moon. Maybe their technology is indeed still there. And this isn't just something I made up. In 2013, 2 physicists argued in a peer-reviewed paper that we should search for alien artifacts on the moon. Their reasoning was that the lunar surface changes incredibly slowly, which is both great for observations and great for preservation of whatever was doing the observation. They estimate that an object a few tens of meters across could take hundreds of millions of years to disappear through impacts. Concretely, they say we might find instrumentation deliberately installed to monitor Earth or a dormant probe awaiting contact. This search still hasn't been done. We also don't have a database dedicated to moon anomalies. anomalous moon observations are usually lumped together with general UAP sightings. I think it'd be a good idea to keep these separate because if you're looking to explain them, these explanations would have to be very different. I mean, look, the European Union has a database for potato types. I feel like moon UFOs could get at least a spreadsheet. In other news, a physicist just wrote a paper claiming that some of the observed unidentified anomalous phenomena are dark matter. Chances are, if we ever find actual aliens, physicists will explain their previously unknown type of dark matter. Do collapsing stars create universes? And if so, could our universe have been created this way? This idea recently made headlines, and I got a lot of questions about it. Scientists propose that entire universes can form inside collapsing stars. We may need new physics. Scientists say mini-universes could form within dying stars. A dying star could trigger the birth of a new universe, scientists say. So, let's have a look. Usually, when a star collapses, it forms a black hole whose defining property is the existence of an event horizon from within which nothing, not even light, can escape. Black holes are often portrayed as objects where a lot of mass is compressed into a small volume, so a very high mass density. But this isn't true. The larger the radius of the black hole, the smaller the average density. In fact, the density at which a black hole horizon forms can be lower than the average density in our entire universe. This is why we might actually sit within a huge black hole. We just haven't noticed because on the inside we can't see the horizon. Mathematically, it's totally possible that we're inside a black hole, but it brings up the question of, well, how did we get there? What does the math say about that? Again, the mathematics says it's possible. There have been various proposals that demonstrate how it could happen that the inside of a black hole generates a new universe, one that then undergoes a Big Bang scenario similar to the one we think happened in our universe. The idea isn't even new. It's been around since the 1970s, and it's appealing because it'd solve two problems at once. It'd explain what happens inside black holes, and it'd explain the origin of our universe. Now, what about the new paper? The authors of the new paper that just made headlines describe a new solution to Einstein's field equations, the equations of general relativity. This new solution describes matter that collapses under the pull of its own gravity. Normally, this matter would form a black hole. In their setup, however, the inside of the collapsing matter begins to expand like a universe would after the Big Bang. And because of this expansion, the horizon never forms. It's basically a black hole origin story without the black hole. And this is what the headlines were about. One does not get a new universe inside a black hole. You get something resembling a temporarily expanding universe, but no black hole. Okay, but wait, you may ask. How can it be that physicists don't agree on what happens when a star collapses? Are they just bad at maths? Well, some of them are, but in this case, that isn't the issue. The issue is instead a general ambiguity in our understanding of space-time. You see, Einstein's equations tell you how space-time behaves, but you can patch together different regions of space-time. You can basically remove the inside of a collapsing star or a black hole and attach something else, for example, an expanding universe or a wormhole to Andromeda or a bookshelf. Mathematically, you can make this all work out. But which of them is physically correct? In a situation like this, physicists normally default on the simplest possible solution, the one with the least extra assumptions. But for stellar collapse, this gives you a singularity on the inside, a place where the curvature of space-time becomes infinitely large. Physicists don't believe that this is what's really going on, and this is why you see so many speculations about other solutions like the one in the new paper. And this is also why I give this paper a 9 out out of 10 on the bullshit meter. It's mathematically fine, but physically it's fumbled together to give a result that they wanted to have, not a result that's remotely physically plausible. This is not illegal in theoretical physics. It is, however, the reason the bullshit meter needs regular maintenance. That said, I want to be clear that this is indeed possible, that collapsing matter or black holes create new universes. It's also possible that this is how our universe came about indeed. However, we currently have no good reason to think this is so. It's just one of many possible things that you can mathematically write down, but that we can't tell apart by observations. In summary, there are more things in mathematics, Horatio, than are dreamt of in your philosophy. News like this doesn't come every day. Scientists have discovered a new type of matter. This is potential material for a Nobel Prize. Let's have a look. Crystals are especially regular arrangements of matter, and they come in many forms. We value them not just because they're pretty, but because many of them have special properties. The most widely used one is probably crystalline silicon, which is used in microchips and solar panels. But crystals are also used for some types of lasers and precision clocks. Diamonds, because they're so hard, are used for some types of saws and cutters. High-performance turbine blades are often made of crystals because that makes them more durable. Metal organic frameworks, which won last year's Nobel Prize in Chemistry, are also a sort of crystal. They can selectively trap molecules and catalyze chemical reactions that makes them super useful for the chemical industry. The authors of the new paper now were studying a ferroelectric crystal. That's a normal, regular and periodic crystal lattice with a special property. In a ferroelectric crystal, you have tiny regions in which the average positive electric charge is somewhat displaced from the negative electric charge. These regions are called domains, and they each have a preferred electrical direction. It's similar to magnetic domains in ferromagnets. The important part is that this direction in a ferroelectric crystal can often be flipped by applying an electric field, and it can remain flipped after the field is removed. This is what the authors of the new paper work with. They used one of those materials which can become a ferroelectric crystal when cooled. They cooled it and saw the ferroelectric domains appear. So far, so normal. Then they cooled it further and something amazing happened. In the surface layers of the crystal, the ferroelectric domains arranged into long strands that passed over and under each other. They formed a three-dimensional weave. This weave spontaneously formed at about 17 degrees Celsius. Yes, you heard that right. That's 17 degrees Celsius, not Kelvin, Celsius. According to my husband, this counts as room temperature. They checked this by probing the crystal with polarized light and taking microscope images at different depths. So this is not just lines that happen to cross when you look at them from above. It's really a three-dimensional structure. They also found that if they heat the crystal and cool it again, it produces a weave again, but in a different pattern. Once the pattern has formed, though, it remains stable as long as the temperature stays roughly constant. But wait, that wasn't it. They also figured out that they can change parts of the woven pattern with a laser. The laser made parts of the weave disappear and rearrange itself. That worked with a green laser, but not with infrared, so it's not just heating. So you have a material that spontaneously forms a pattern. The pattern's stable and can be changed with light. This makes it potentially useful for many applications. The authors suggest new types of memory storage and neuromorphic computing, which means computer hardware designed to process information in ways inspired by neural networks. Now, this is a small lab study and applications are far away, and while the laser did alter the weave, they could not control just what it did. So if you want to use that to store memory, it's not great. You might just remember that you were supposed to remember something, but not what. Still, I'm not joking when I say that this is the sort of discovery that can become Nobel Prize material. Strands of domains have been observed before in some materials, but not as regular as this. So this is a genuinely new discovery, and who knows what new electrical or optical properties such crystals will turn out to have when further studied. Really, I think we've just witnessed the beginning of an entirely new research area. Quasi-crystals and the metal-organic frameworks, which I mentioned earlier, quickly made it from a quirky discovery to practical uses and a Nobel Prize as well. I give this a 0 out of 10 on the bullshit meter. It's not my research area, so I can't properly judge the experiment, but it seems unlikely to me that there's something seriously wrong with either the data or the interpretation. Part of the reason I'm telling you about this is that I think material science is super underrated. There's a reason that we now have so many AI startups that want to work on the discovery of new materials, because this science has a huge impact on our daily lives. Because think about it, we name historical epochs not by food sources or artistic skills, but by our ability to shape materials. The Stone Age, the Iron Age, the Bronze and the Steel Age. Nobody talks about the excellent Soup Age. Then maybe that's still to come. Still, if someone born 10,000 years ago came to visit us, I believe the first thing they'd be surprised by would not be phones or cars. It'd be concrete, glass, mirrors and plastic. It'd be microfibers, optical fibers and Teflon. It'd be all the brilliant pigments, paved streets, stainless steel and anodized aluminium. And then we'd give them a plastic fork that snaps in the potato salad. Welcome to civilization. A nuclear fusion startup in New Zealand has just put forward the first new idea for the nuclear fusion technology for decades. They're called OpenStar Technologies, and they're the only startup which works on an approach that's called a levitating dipole that everyone thought was fundamentally flawed. But they've turned the bug into a feature. Let's have a look. OpenStar Technologies just published a paper with a new design for a commercial nuclear fusion machine that they say is predicted to produce 208 megawatts of net electric power. To put this into context, that's about the power output of a small gas power plant. They call their design Tamanui, a name that's derived from the Maori word for sun. But what's new about it? OpenStar has bet on the levitating dipole approach. That's a variant of nuclear fusion that works with magnetic confinement. The usual approach is a tokamak or stellarator, in which one has the fusion plasma inside strong magnets that usually form a sort of torus. The biggest challenge for these approaches is to keep the plasma levitating inside the containment vessel, because it's super hot, and when it touches the reactor walls, that will damage them. In the dipole fusion reactor, the plasma vessel does not have a hole in the middle. Instead, one levitates a big torus-shaped magnet inside the vessel, and this magnet is what creates the dipole field. If the magnet's superconducting, the field can be strong enough to trap the plasma and heat and compress it, hopefully enough for fusion to set in. The idea is kind of similar to the tokamak, but putting the magnet inside the reactor vessel has two major advantages. The first is that it removes some instabilities in the plasma just because the geometry of the magnetic field is different. The second is that because it's easier to keep stable and the magnet is in the middle, you need fewer of the magnets, and that makes it cheaper. But as usual, there are trade-offs. The issue is that this idea brings in a new instability, which is that now you have to keep the magnet in place. Worse still, you now have the magnet inside the plasma, and that makes it much more likely it'll get damaged. The biggest problem is the fast neutrons that are produced in deuterium-tritium fusion. Because they're neutral, they can't be trapped or redirected with the electric and magnetic fields. They'll degrade the magnet quickly. Now, one could use different fuels instead, like, for example, boron, that not produce neutrons or not as many neutrons. But the problem with such other neutron-free fusion tritium fuels is that the temperature one must reach is dramatically higher than for deuterium-tritium fusion, which is also bad. And this is why, in a nutshell, the dipole fusion approach pretty much hasn't been pursued, though it's been around since the 1980s. MIT then had a small test device which ran from 2004 to 2011, and the Japanese have a small research facility, but that's basically it. But if not the levitated dipole, then what's new? And the news is that OpenStar has come up with a way to make this idea compatible with deuterium-tritium fuel. Their idea is no groundbreaking new physics, it's rather a very down-to-earth management proposal. They say shield the magnet as well as you can and then make sure that you can replace the shield when needed, so the weakness of the approach becomes a maintenance problem. Concretely, they say they want to use a superconducting magnet of barium and copper, that's fairly standard. Around the magnetic coil, they have a shield of tungsten and boron carbide. This is because this material can withstand a lot of heat and it's also good at absorbing neutrons. That too is fairly standard. What's new is that their magnet is not one block. It has a main section and an outer section. They accept that this outer section will get damaged and instead try to find a way to cheaply replace it in regular intervals. So they plan on a mechanism by which, after about a year, the entire magnet module is removed from below by robots and then put in a radiation-safe room to replace the damaged parts. They estimate that this replacement itself would take about 2 weeks and that this can be done about 10 times, after which the other parts have to be replaced as well. It's basically the fusion reactor of Theseus, except every plank is radioactive and the philosopher has died. In summary, OpenStar has not solved nuclear fusion, but they have proposed a serious engineering route for a strange old fusion idea that previously had a big problem. Also, I think there's a bigger lesson here. Other startups should spend more time thinking about the question of regular maintenance because it'll be a major contributor to the running cost. And next time your computer runs into a problem, just try turning it off and replacing the radioactive middle bit. Thanks for watching. See you tomorrow.